Have you ever stopped to think about how your computer can stream music, have a dozen browser tabs open, and let you edit a document all at the same time without just, exploding? Well, today we're going to pull back the curtain on the hidden genius that makes all of that possible: memory management.
I mean, seriously, think about it for a second. You've probably got a web browser open with 20 tabs right now, a music app playing in the background, a document you're working on, maybe even a game running. How on earth does your machine juggle all of that without just giving up? Well, the answer is all thanks to this brilliant piece of engineering called memory management.
All right, so to really get this, we got to start super simple. Let's just forget all the technical jargon for a minute. Just picture your computer's memory as a long row of boxes.
Yep, that's basically it. At its core, your computer's RAM is just a massive, organized collection of these boxes. And every time you fire up an app, it basically goes to the operating system and says, hey, can I get a few boxes to store my stuff? It's a really simple idea, right? But, and this is the key, how the computer hands out those boxes is where the real story begins.
Okay, so let's rewind a bit. How did computers used to hand out these boxes? Well, back in the day, the rule was super straightforward, and honestly, it kind of makes sense when you first hear it. So, if a program needed, let's say, 4 boxes of memory, the operating system had to go and find 4 boxes that were all sitting right next to each other, in a perfect, unbroken line. No gaps allowed. It had to be one solid chunk. Sounds simple, right? Yeah. Well, that simple little rule, it ended up causing a huge problem.
And this is where things start to fall apart. See, on paper, that approach sounds all neat and tidy, but in the real world, with us opening and closing apps all the time, it just created total chaos.
Let me walk you through it. Just imagine our memory only has, say, 8 boxes total. Program A comes along and grabs 4. Then Program B takes 2. And Program C takes the last 2. Okay, memory's full. But then, you finish with Program A, so it leaves. Now there's a 4-box hole. Then you close Program B. Now there's another 2-box hole. What you're left with is, well, it's a mess. Just these scattered empty spaces. Okay, now here's the kicker. A brand new program, let's call it G, shows up, and it needs just 3 blocks. Now, if you do the math, we have 4 blocks free in total. So, plenty of room, right? The question is, can it actually run? And the answer, believe it or not, is no. The program can't launch. Even though there's technically enough free space, there's no single chunk of space that's big enough. All that free memory is just, it's broken up into these useless little islands.
This whole mess, this disaster, actually has a name. It's called external fragmentation. And yeah, it's pretty much the villain of this story. The cake analogy here is perfect. It's like you have all the ingredients you need, but the flour is in one kitchen, the eggs are in another, and the sugar is in a third. You have enough stuff, but you can't get it all in one place to actually bake the cake.
So yeah, to sum it up, this old system was just broken. You had this fragmentation, you were wasting good memory, and apps would just fail to launch when they shouldn't have. And the only fix? It was this thing called compaction, which basically meant stopping everything to shuffle all the memory around. I mean, can you imagine? It was ridiculously slow. We absolutely needed a better way.
And that brings us to the hero of our story, a totally genius solution called paging. And this right here, this is what's running inside pretty much every computer, tablet, and phone you use today.
And this slide just nails the difference in thinking. The old way was like, you have to give me one big, continuous block, super rigid. The new way just says, you know what? I don't care. Give me small pieces from anywhere you've got them. I'll figure it out.
So, here's the secret sauce. The system takes all the available memory and chops it up into these small, identical-sized blocks. We call them pages. Then it does the exact same thing to the program you want to run. It breaks the program itself into pages that are the very same size.
So, how does just chopping everything up solve that huge fragmentation problem we were just talking about? Well, it all comes down to finally throwing out that one single, really restrictive rule.
But hold on a second. You might be thinking, if a program is scattered in pieces all over the place, how does it even work? I mean, the program itself is written to think it has one nice continuous block of memory. So how does the computer create that illusion when the reality is a total mess?
The magic trick is something called the page table. The best way to think of it is like a special address book or a map that the operating system keeps for every single app. So when the program says, hey, I need my second chunk of data, the OS just glances at the page table, sees, oh, that's actually over in memory slot 5, and grabs it. It's a translator. It translates the program's simple, neat view of the world into the messy, scattered reality. And it does this so incredibly fast, the program has no idea what's happening.
Okay, so let's rewind to that disaster scenario from before. Remember Program G? It needed 3 blocks and couldn't run? Well, with paging, the OS just looks for any 3 empty pages. It doesn't care where they are. It finds one here, one over there, and one way at the end. It grabs them, gives them to Program G, and boom, problem solved, just like that.
And the advantages here are they're huge. External fragmentation, gone completely. Every single free page is now fair game, so there's basically no wasted space. You don't need that awful, slow compaction process anymore. And giving memory to new apps becomes super fast and easy.
All right, let's do a quick showdown. Let's put these two systems right next to each other so you can really see the difference.
So you had the old system, it was clunky, it was wasteful, and you just couldn't count on it. It just couldn't keep up with modern computing. And then you have paging. It's the total opposite. It's flexible, it's efficient, and honestly, it's the reason we can multitask like we do every single day.
Look, if you take away just one thing from all this, let it be this analogy. The old system, it's like a hotel that will only rent you an entire floor. If you just need one room, too bad. The new system, paging, is like a smart hotel. It'll give you any empty room on any floor, and it just keeps a master list of where everyone is. It's just a way smarter way to manage the space.
And that really is the heart of it. Just by getting rid of one simple and what seemed like a logical rule, that memory had to be all in one piece, engineers completely changed the game. They unlocked the door to the kind of powerful, smooth multitasking that we totally take for granted now. So the next time you've got a dozen apps running without a single hiccup, you'll know exactly what's going on behind the scenes. It's the magic of paging.